Hi there, students. This is Dr. John, your physics and math professor. We are working on transformations. In a previous video, what I worked on is a vertical stretch. Notice here we had y is equal to 2 sine x. Well, what we do is we look at the original function, which would be y is equal to sine x, and then say whatever the values of, I've drawn out a sine curve here, whatever the value of sine x is, we're going to multiply that by 2. So we're going to take this, the y value, and stretch it. So this would be called a vertical stretch. We use that for a stretch or a compression. If we multiply by 1/2, we still call that a stretch, just so we don't use too many words. We want to only use stretch, reflect, translate. S-O-R-T, if you want to remember it that way. This is how to sort them. Start with the stretch and the reflections and then the translations. You can actually do the stretches and reflections at the same time if you use my mathematical method here. This is sort of obvious here. We're multiplying all the y values by 2. But what if we multiply both sides by 1/2? We get 1/2 y is equal to sine x. Now notice here, for whatever value of x you have, you want to have the same value of y, because this relationship, this function here has to stay the same, which means you have to double the y, which means you have to stretch the y. If you put a fractional number, a number less than 1, then y has to be bigger than 1. If this number is bigger than 1, then y has to be less than 1. So you're going to have to stretch. So this is the opposite. If you put this number right in front of the y, it's sort of the opposite of that number. Flip it over. If it's negative, of course, you leave the negative there. Then you make it negative flipped over. So over here, notice that the numbers now are directly in front of the x. Now what we're going to look at is we're going to look at a stretch or reflections or whatever in the x direction. Previously, it looked like it was on this side, but really it was associated with the y. So now we're going to associate it with the x. And because there's a function surrounding the x, there's usually a function surrounding the x, we can't just pull the number out like we could here. We could take this number 2, pull it to this side very easily. We can't do that here, so we have to leave it in with the x. So in the same way as this over here, notice this is right in front of the x, so what effect will that have on the x? Just like this here, this 1/2 in front of the y, we have to double the y, so here we have to cut the x in half. So we're going to have to take this all and squeeze it that way. So this point here is going to become this point here. This point here is going to be somewhere over here. This point is going to be halfway, like I said, right there. And this one's going to be right there. So this is going to be still a 0, and this is still going to be a 0, but it's going to do this. And then this here is still going to be a 0. Notice it goes through the period or an entire oscillation of up and down in half the time, because I put that 2 in there. So really what this is here now is I have compressed the x value, where I've multiplied all the x values. I've left the y values the same, multiplied all the x values by 1/2. Let me do another illustration for you over here. I'm going to redraw a couple of things, and that'll help us to understand this a little better. So here we have another function for you. This is the square root function. What are a couple of points on that square root? Well, one point here is 0, 0. One point here is 1, 1. One point here is 4, 2. I wrote them really tiny there. So this is the generic square root, the base function. Now let's say we wanted to draw something like this. Now we want to do the root of minus x. Minus x would of course be a stretch, because it's associated with the x, a stretch in the x direction, but it would be a negative stretch. A negative stretch, a stretch of -1. A stretch of -1. What would that look like? Well, it would tend to look something like this. What would we do to the different values here? Remember, the y values stay the same, but what happens to the x values? Well, each of the x values has to be multiplied by -1. So we're going to still be 0, 0 here. That one stays the same. We're stretching it, and this is sort of pinned. This axis, everything that touches this axis is pinned, and we're stretching from that point onwards. And then this one over here, the x value is going to be -1 now, 1, and here it's going to be -4, 2. Does that seem to match what we've sketched? Here 1, here -1, 1, 1, 2, 3, 4, somewhere over there, -4, 2. This is the root of minus x. So let's say we wanted to sketch the root of 1/2 x. Here's the base function. Here's the base values here. I drew this one in black. I drew these values in black here. And remember, if we're putting it directly with the x, it's going to affect the x values. but we have to double the x. We have to double the x to get the same y. So we're going to have to take everything and multiply it by 2. So whatever x values there are, we're going to have to multiply them by 2. So the x value here would stay the same. It's still 0. The y value stays the same. Here, we're going to the original one. We're multiplying this by 2, so it's going to be 2. The y value stays the same, and this one's going to be doubled. It's going to be 8, 2. Let's start off by putting this point there. Then this point here would be 2, 1. So it's 2, 1 now. Notice this point is shifted that way. It's stretched this way. The other point's going to be a little harder. 4, 5, 6, 7, 8. And barely fit it on there. So it's going to be right there. So this point is stretched this way. The further you get from the origin, the more you're going to stretch it. So if you had to draw this, something like this. It's very hard actually to tell the difference between a root of x function, like the black one here, and a root of 1/2 x, like the green one here. So it's nice when we're doing it for illustrative purposes that I'm using specific functions to show certain things. I just wanted to show you a couple of these things. So sometimes when you're graphing it or you're drawing it on there, it may look very close to the original, but it's still worth sketching it out, and you can just see what those individual points do for you. This video was a little bit simpler, but we're going to see you in the next video and hopefully show you a bunch of examples that will help you walk through this somewhat difficult stuff and make it much easier for you. So like and subscribe, and I'll see you in the next video. Bye-bye.